In the following moles and titration question taken from the ATP past papers of O levels, the question is dealing about finding the percentage composition, and it's related to redox titration. So the question states that R is a mixture of iron 2 sulfate and iron 3 sulfate, which means that it's a mixture of two compounds. One is iron 2 sulfate, which is FeSO4, and the other one is iron 3 sulfate, which is going to be Fe would be 3 plus and SO4 would be 2 minus, so it's going to be Fe2 SO4 3. So using the crisscross method, I figured out the formula. This is iron 2 sulfate, Fe being 2 plus, SO4 being 2 minus, so the charges cancel out, so the formula is FeSO4. Over here in iron 3 sulfate, Fe is 3 plus, SO4 is 2 minus, so Fe, there would be 2 iron ions having 3 plus charge, and there would be 3 sulfate ions having 2 minus charge. So those are the formulas of the compound. So it's a mixture of two substances, and this is called R. This substance over here, this mixture, is going to be called R. In the next part, it states that a student determined the percentage of iron 2 sulfate in the mixture using 0.02 mole per decimeter cube aqueous potassium magnate 7 solution S. So what he's doing is he's trying to find the percentage of FeSO4 in this mixture. Now, the first thing is he's saying that potassium magnate 7, which is purple, oxidizes the iron 2 ions. What is meant by the term oxidation is that the Fe2 plus ions would lose electrons, and when they lose electrons, they're going to form Fe3 plus. So that is what is meant by oxidation. Oxidation is loss of electrons. So iron 2 ions readily oxidize to iron 3 plus ions when you add this oxidizing agent, which is potassium magnate 7, which is KMnO4. It's a very powerful oxidizing agent. So the first part of the question states, suggest why potassium magnate 7 does not react with iron 3 ions. The reason why it cannot react with Fe3 plus ions is because Fe3 plus has already lost electrons. So Fe3 plus it cannot lose more electrons, so it can't get oxidized. So when a thing that is getting oxidized is called a reducing agent. So Fe3 plus is not a good reducing agent, which basically means that Fe3 plus has already lost too many electrons. It has lost 3 electrons, so it is incapable of losing more electrons, which is why potassium magnate cannot possibly oxidize Fe3 plus. It could do that to Fe2 plus, because Fe2 plus can still lose a few electrons and become Fe3 plus, but Fe3 plus has already lost too many electrons. It would instead actually be attracting electrons because it has a very high positive charge. So it's not capable of losing electrons, which is why it's a very terrible reducing agent. So that's the answer to this part. In the next part, a sample of R was added to a previously weighed container, which was then reweighed. So given the mass of the container plus R in it, which has a mass of 18.04 grams, and you're also given the mass of the container. In the next part, you're asked to calculate the mass of R used in the experiment. So you just need to subtract 18.04 and get rid of the mass of the container from this mass over here. So you're going to subtract the two values, and using my calculator, the value that I'm getting is 6.08 grams. So that is the mass of R. So let's write down the mass of R over here as well. The mass of R that's being used is 6.08 grams. Moving on, the question states that the sample of R was placed in a flask. So you're placing R was placed in a flask, a volumetric flask, a conical flask probably, and it's dissolved in 100 cm cube of dilute sulfuric acid, and the solution made up to 250 cm cube with distilled water. So it's basically a volumetric flask that has a volume of 250 cm cube. So it's being dissolved in 100 cm cube of dilute sulfuric acid, and the solution is then made up to 250 cm cube with distilled water. So we're going to sketch this part. This solution was then called T. So I'm going to show this part using a sketch. So here is my volumetric flask over here. I'm going to put this R, this 6.08 gram sample in this. I'm going to dissolve it in sulfuric acid. Remember, dissolving it in sulfuric acid would not produce a reaction because FeSO4 already has sulfate ions, so there wouldn't be any reaction. So it's being dissolved. It's dissolved in H2SO4. So H2SO4 would not react with FeSO4 or Fe2SO4 Instead, it's going to make the solution acidic, but it would try and dissolve. So we're going to get a solution, and he's adding distilled water and making the solution up to 250 cm cube. So now we have a 250 cm cube solution, and the solution is being called, the name given to the solution is, this is solution T. So the name that is being given to the solution is T. And what does T contain? It contains two types of ions. One is Fe2 plus aqueous ions. They would be present coming from FeSO4 when you dissolve FeSO4, and the other one is Fe3 plus aqueous, and that is coming from the iron 3 sulfate salt that is being dissolved in this volumetric flask. So these two ions are present in the solution T, which has a volume of 250 cm cube. And solution T was obtained when the sample of R, which is over here 6.08 gram sample, was dissolved in sulfuric acid. In the next part, reading the question, 25 cm cube of T was transferred into a conical flask. Now we are transferring this 25 cm cube of T, which we just made over here. We made a 250 cm cube T, and now we are transferring 25 cm cube of T into a conical flask. So let's show that on our sketch as well. So here's my conical flask, and I'm going to transfer this solution T now into this conical flask. But remember that only 25 cm cube of T is being transferred. And what does T contain? It contains Fe2 plus ions, and it also contains aqueous ions, and it also contains Fe3 plus aqueous ions. Plus it also contains the acid that we added, sulfuric acid that we added initially. So that's also present, but more importantly, Fe2 plus and Fe3 plus aqueous ions are present in this solution T. So this is the amount of T that has been added, and he's asking what piece of apparatus would be used to transfer the volume of T. Now when you're transferring solution, especially 25 cm cube, a pipette would be used to transfer. Pipette acts like a dropper. You fill it at one end by using a suction device. You fill it over here, put it in this solution T, this 250 cm cube solution T. You take it out and you drop the liquid into this conical flask, which is made over here. So a pipette would be used to transfer 25 cm cube of T. In the next part, he's saying the solution S was put into a burette and run into a conical flask containing T. So we're going to put solution S into a burette. And what was solution S? Solution S was initially given to us. They explained that solution S was mentioned over here. It was a 0.02 mole per decimeter cube aqueous potassium magnate 7 solution, which was called solution S. So let's draw a burette and fill it with this solution S, which is 0.02 mole per decimeter cube potassium magnate 7. So here is my burette, and I'm going to put solution S in this burette, which is basically KMnO4. So KMnO4 is put into this burette, and my flask contains these Fe2 plus and Fe3 plus aqueous ions. They are present in this solution over here. Now the next part of the question states he's basically putting KMnO4 and adding KMnO4 to this flask over here. Now in the next part, he's asking what was the color of the solution in the conical flask before S was added. Now remember that this conical flask over here contains Fe2 plus ions and Fe3 plus ions. So if it contains Fe2 plus ions would give you a green solution. A green solution would be present in the conical flask because Fe2 plus has green color, so there's going to be a light green solution. And KMnO4 is purple. Now remember that when you add KMnO4 is an oxidizing agent, and oxidizing agents oxidize substances. And previously in the previous steps we also figured out that KMnO4 is not going to react with Fe3 plus. It can't oxidize Fe3 plus. The reason it cannot oxidize Fe3 plus is that Fe3 plus has already lost a lot of electrons, so you can't really oxidize it. But it can oxidize Fe2 plus and convert it into Fe3 plus. So the KMnO4 that's being added is basically reacting with the Fe2 plus that's present in this solution over here, not the Fe3 plus. So this Fe3 plus is not going to react. It's reacting with Fe2 plus. And KMnO4 is purple in color. So this KMnO4 over here has a purple color. And when this purple KMnO4 reacts, when it's put into this conical flask, it's going to react, it's going to change into colorless. So as long as the reaction is happening, you're adding KMnO4 KMNO4 goes and reacts with the Fe2 plus in this flask, it's going to go colorless. The end point would be reached when you add KMNO4 and there is no more Fe2 plus in this flask. All the Fe2 plus has reacted. Then this purple colored KMNO4 has nothing to react with. So if you keep on adding KMNO4, once all the Fe2 plus has reacted, the KMNO4 would remain purple, and this flask, the solution in the flask would start to change color because of the purple KMNO4 being added. So at the end point would be shown when the color, what was the color of the solution in the conical flask at the end point? It would start to go purple, because at the end point, when you're adding KMNO4 to this flask, there is nothing left to react, and that KMNO4, purple KMNO4, would start turning this flask purple as well, because it's not reacting anymore. So the final end point of this titration would be that you would see a purple colored solution in the conical flask over here. Now in the next step, the question states that 3 titrations were done, and the diagrams below show parts of the burette with the liquid levels at the beginning and end of each titration. Over here is basically the liquid that he's mentioning is KMNO4. On the diagram, I'll explain this to you that he's adding KMNO4 into this flask, which contains these Fe2 plus and Fe3 plus ions. And the amount of KMNO4 that's being added, that is being noted down. See, 3 separate titrations are done. This is called titration. You're adding a liquid KMNO4, aqueous KMNO4 from a burette into this conical flask, and you're reacting the 2 substances together. So the amount of KMNO4 that's being added, the volume of KMNO4 that's being added, is measured. And he's done 3 separate titrations. 3 separate titrations are done to improve accuracy of the result, because taking average of many different experiments would give you a more accurate result. So this is the first titration, where the initial burette reading is given and the final burette reading is given. This is the second titration, with the initial burette reading and the final, and the third titration. And you're given a table which you need to fill up based on these values. You're going to figure out how much KMNO4 is being added. So looking at the first titration, the initial burette reading is 0 centimeter cube, and the final burette reading is 26.3 centimeter cube. Always read the lower meniscus. So the initial burette reading is 0.00 centimeter cube, and the final burette reading is 26.30 centimeter cube. Remember to take burette readings to 2 decimal places, because that's the accuracy of the apparatus. So the amount of KMNO4 that's added in this experiment is, you're going to take the difference. Initially the burette was filled up to the 0 centimeter cube mark. Once the titration had ended, the burette reading showed a level that was 26.30 centimeter cube. So the amount of KMNO4 that's added is going to be the difference, which is going to be 26.30 minus 0.00, which is going to be exactly 26.30. So that's the amount of S or KMNO4 used in the first titration. Moving to the second titration, the initial burette reading is 3.6, so that is 3.60 centimeter cube, and the final burette reading is giving us a value of 29.40 centimeter cube. So the amount of S that's been added, so I'm going to use my calculator and I'm going to subtract the 2 values. It's going to be 29.4 minus 3.6, and the value that I get is 25.80 centimeter cube. So that's the amount of KMNO4 used in the second titration. And moving to the third titration, the initial burette reading is 21.60. So that's my initial burette reading. It's 21.60. My final burette reading is 47.20 over here. So that's 47.20. Taking the difference, 47.20 minus 21.60, the value that I get is 25.60 centimeter cube. Now moving to the next part, I figured out the 3 titration results. The first experiment, you put 26.30 KMNO4, and the second one you put 25.80, and the third one you put 25.60. So that's the amount or volume of KMNO4 that's being used in 3 experiments. Now I have to pick the best titration results, and the best titration results are the ones that are close to each other. So if you look at the 3 values, this first value is slightly off. It's further away from the other values, which means that there must be something going wrong in this experiment over here. So we're going to ignore this value, The best titration results are the ones that are always close together. That shows consistency. So these two values are your best titration results. And in the next part, after you've ticked the best titration results, using these results, find the average volume of S that was used. So we're going to find the average volume of KMNO4 that's used using my best titration results, which are these two. So I'm going to just take the average value. So it's going to be 25.80 plus 25.60, and I'm going to divide the whole thing by 2. So the average volume of S that's being used is 25.70 centimeter cube. So that's my average volume of S that is used. So I'm going to add that on my sketch as well. So the volume of S KMNO4 that's being used is 25.70 centimeter cube. So that's the volume of S that's being used. Another thing that needs to be noted as well is that you also know the concentration of this KMNO4, which was given in the first few lines of the question, which was 0.02 mole per decimeter cube. So you now know two things about the KMNO4 that's being added. You know the concentration of KMNO4 that's being added, and you also know the average volume of KMNO4 that's being added. So if you know the volume and you know the concentration, then you can find the moles. So in the very next step of the reaction, that is exactly what is being asked. He's given us that S is 0.02 mole per decimeter cube potassium magnate 7, and you're asked to calculate the number of moles of potassium magnate 7 present in the average volume of S. So we know that the volume that's being used is 25.70 centimeter cube, and we also know the concentration, which is 0.02 mole per decimeter cube. So that's also known. Now the formula for moles is moles would be concentration multiplied by volume. So I'm going to multiply the concentration, which is 0.02, by the volume, which is 25.70, but it should be in dm cube. So I'm going to divide that by 1000, and I'm going to use my calculator to solve this now. And the answer that I get on my calculator is it's 5.14 times 10 to the power minus 4 moles. So that is the moles. Those are the moles of KMNO4 that are being added. So I'm going to add that to my sketch as well. So the amount of moles of KMNO4 that are being used are 5.14 times 10 to the power minus 4 moles. So that is the quantity of KMNO4 that's added into this flask over here, which contains Fe2 plus ions. In the next part, part G, the question states that 1 mole of potassium magnate 7 reacts with 5 moles of iron 2 sulfate. So he's given us the ratio in which potassium magnate 7 and iron 2 sulfate or iron 2 ions are reacting. So it's 5:1. So let me show that on the sketch over here. What the question means is that if you have 1 mole of KMNO4, so if you have 1 mole of KMNO4, then that would react with 5 moles of FeSO4 or Fe2 plus ions. So we know the ratio now, and the ratio is 1 mole reacts with 5 moles of FeSO4, but we have 5.14 into 10 to the power minus 4 moles. So what is the quantity of FeSO4 in the flask over here? So the ratio is given, 1 reacts with 5. So what would 5.14 into 10 to the power minus 4 moles react with? So using simple ratios, I'm going to try and solve this question now. I know that, and let's use the ratios over here, Fe2 plus, or it would be better if we just write the entire thing, which is FeSO4 ratio KMNO4, and he said that 1 mole reacts with 5 moles. So we have 5.14 into 10 raised to the power minus 4 moles of KMNO4 in a burette. So what would be the quantity of FeSO4 that would react with it? So using the unitary method, using ratios, simple ratios, X would be equal to, X is the number of moles of FeSO4, they would be equal to 5.14 times 10 to the power minus 4 multiplied by 5. And using my calculator, the answer to this part is going to be So the answer that my calculator gives is 2.57 into 10 raised to the power minus 3 moles of FeSO4 would be in the flask. So let's put that over in the sketch as well. So it's going to be 2.57 into 10 raised to the power minus 3 moles of FeSO4 in the flask over here. So it's 1 reacting with 5, so 5.14 into 10 to the power minus 4 would react with these many moles of FeSO4 or Fe2 plus ions. In the next part, moving to part H, the question states calculate the number of moles of iron 2 sulfate in 250 cm cube solution. Now, this was our 25 cm cube solution of T that we took and titrated, and we found out that it had 2.57 into 10 to the power minus 3 moles. Now he's asking us to find the moles in 250 cm cube of T. Remember that this 25 cm cube solution in the flask was taken from that 250 cm cube. So we're going to use ratios again. So if 25 cm cube T contains 2.57 times 10 to the power minus 3 moles of FeSO4, then how many moles would be present in 250 cm cube T, which was the original sample of T? So how many moles would be present in that? So if 25 cm cube contains 2.57 into 10 to the power minus 3, so you can use simple ratios. 250 is 10 times that quantity, so the number of moles would be 10 times that many. So you can use simple ratios. So you're going to multiply 2.57 times 10 to the power minus 3, and you're going to multiply the whole thing by 10. The number of moles would be 10 times that quantity. So the answer that you're going to get is going to be 2.57 into 10 raised to the power minus 2 moles. So the 25 cm cube solution contains these many moles. The 250 cm cube original solution from which this solution was taken would contain 10 times that many moles. So let's write down the moles of Fe over there, Fe2 plus or FeSO4 over there. They're going to be 2.57 into 10 raised to the power minus 2 moles. That would be the amount of moles of FeSO4 or Fe2 plus in the flask, in the volumetric flask over there. Now we've been able to find the moles of FeSO4 in this volumetric flask over here. They were 2.57 into 10 to the power minus 2 moles, and all these moles were coming from this original quantity of R that was dissolved and from which the solution was made. So we've basically figured out the moles of FeSO4 in this sample R, because all the moles of FeSO4 in this flask over here are coming from this sample R. So in the next part, he's now asking us to find, using your answer to H, this previous answer, calculate the mass of iron 2 sulfate present in solution T. So we know the moles of FeSO4 in the solution T. So moles is equal to mass over MR. Moles is given, so that's 2.57 times 10 to the power minus 2. Mass is unknown. Moles is equal to mass divided by the molar mass, and the molar mass is already given. It's 152. So using my calculator, mass would be, if I multiply the moles by the molar mass, MR over here, and the answer that I'm going to get is, and the answer is 3.91 grams. So that is the mass of FeSO4 in the sample R that was given to us originally. And in the next part, part J, the last part, using your answers to B and I, calculate the percentage of iron 2 sulfate in the sample of R. So we need to find the percentage of iron 2 sulfate in the sample R. Remember, R originally was a mixture of FeSO4, and it was a mixture of iron 3 sulfate, which was Fe2SO4 3. So it was a mixture of these two salts. And the total mass of this sample of R, let's go back to our sketch. The total mass of this sample R, originally that was given as 6.08 grams, that we calculated in the initial parts of the question. So that is 6.08 grams. Now, after titration and after doing all the calculations, we figured out that FeSO4 has a mass of 3.91 grams. So this thing over here has a mass of 3.91 grams. So we need to now find the percentage of FeSO4 in this original sample of R. So the percentage of FeSO4 would be the mass of FeSO4 in the sample is 3.91 grams. The total mass of the sample of R is 6.08 grams. And I'm going to multiply that by 100 to get a percentage, and using my calculator it's going to be 3.9064 divided by 6.08, and that would be multiplied by 100, and the answer is 64.25%. So that is the percentage by mass of FeSO4 in the original sample of R.